Good afternoon, my dear students of St. John's 5th semester. This is Pharmacognosy and Phytochemistry 2 for the semester 5 students. This is our second class, continuation to the metabolic pathways which we have seen in the last class. Especially we have seen up to aromatic amino acid biosynthesis up to tryptophan, and we have seen the succinic acid pathway and its details. And this today I am just continuing metabolic pathways, in which we are going to discuss about, especially the slide which I am showing to you now. It shows something about amino acid degradation intermediates. This is just a slide which is not showing any type of production of amino acids, aliphatic amino acid from the primary metabolites, but this is an understanding for you to say that even the primary metabolites can produce the aliphatic amino acids through these pathways, and also aliphatic amino acids can be utilized for various secondary metabolites for their production. And you can see that amino acids are also can enter into the various metabolic pathway for the production of energy. So here you can see that it is amino acids have been categorized by glucogenic and also ketogenic amino acids, such that you can see in the slide which shows about the alanine, cysteine, glycine, serine, threonine, tryptophan. All this can converted into pyruvic acid and acetyl CoA, and then it can enter into TCA cycle. And also if you see the ketogenic amino acids, you can see isoleucine, leucine, lysine, threonine, and also it can also enter into acetoacetate. And also there are many amino acids which I have shown in this slide which can enter. For example, you can see arginine, gluco and histidine, proline. These all things can also be entered into alpha ketoglutarate. And succinyl CoA can also be, and it can also enter like isoleucine, methionine, valine, and aspartic acid. So you can see fumarate, oxaloacetate, all the components which comes in the intermediate product of a TCA cycle also responsible for the production of various aliphatic amino acids. So this is just for an understanding for the student, that is, you should know about the primary metabolic pathways and primary metabolites, which are also giving various structure of chemicals which can be responsible for production of other secondary metabolites. So now we are going to the next step, is actually we are going to study about acetate or mevalonate pathway. So acetate pathway or mevalonate pathway is the second very important pathway when compared to the same like succinic acid pathway, how it is very much responsible for all aromatic compounds, aromatic secondary metabolites. This is also very important for the production of various terpenes, steroids, hormones, and various other structural compounds of secondary metabolites are produced by this mevalonate pathway. So as we have been studying in succinic acid pathway also, I just mentioned last class, that is, you should know about the structure of succinic acid so that it will be easy for you to go into the various steps of succinic acid pathway. Here also the same thing, we should know about what is the structure of mevalonic acid and what all the precursor and what all the structure name. Once you are thorough with the theoretical knowledge, and then you can write and see the structures can also be easily you can study. As we are not using any type of chemical catalyst or anything of reagents, we are not using here in biosynthetic pathways. In biosynthetic pathways, we will be having many enzymes which are responsible and cofactors which are responsible for the products. So in that case, it will be very easy for you to remember. Once you know the product, it will be always related to the enzymes, will be always, the names are related to the products usually. So it will be easy for the students to study the enzymes and the product and the various steps which is involved. Once you know and once you follow what I am saying, and when you listen to my audio and this lecture, it will be easy for you to study, and also you can refer various books, and as well as in internet source also you can download, and you can elaborate your knowledge by means of just this is an hints, and this is just an hints and as well as an understanding which is given by me. But there are many things to study from various books and various internet sources. And if you see that mevalonic acid, there is an enzyme which is very much responsible for this mevalonic acid production from acetate, and that is asto-acetyl CoA or acetyl CoA, and you can see that is HMG CoA reductase, that is 3-hydroxy-3-methyl glutaryl coenzyme A reductase. And you can see that what is the importance, we will see that is the enzyme very important. Other enzymes are also involved, and you can see the mevalonate pathway, also known as isoprenoid pathway or HMG CoA reductase pathway. So isoprenoid pathway, there we are going to stop, and we want to understand what is isoprenoid, because this is a very important word here in this mevalonic acid pathway, isoprenoid pathway. Why it is isoprenoid? Because isoprene unit is a very important unit which will formed by means of this pathway, and which will be responsible for various production of terpenes and steroids, hormonal products, and all the things are produced by the basic isoprene unit. So isoprene units are rare. What do you mean by isoprene units? Why it is called isoprene units? Where we have come across this isoprene units? In your smaller classes, your teacher might have told isoprene units are 5-member carbon atom containing molecules, or it's a compound which is named as isopentyl group, or you can say dimethyl allyl group. These are the 5 carbon atom compound group which is the unit of terpenes. Terpenes are always called as monoterpene, diterpene, tetraterpene and sesquiterpene, and there are even many terpenes are always calculated by means of these isoprene units. If there is 2 isoprene units together and it is joined together, then we will say that is monoterpene. If it is 4 isoprene units are there, then we will say diterpene. Like that it is going on. Terpenes are determined. So terpenes having a basic isoprenoid units. Not only in terpenes, this isoprene units is important. Isoprene units are very important for this mevalonic acid pathway for the production of various steroids and the hormonal products and terpenes and various secondary metabolites. And you can see here the pathway is essential pathway in eukaryotics, that means, and some bacteria, unicellular bacteria also having this cycle which takes place. The pathway produced 2 5 carbon atom building blocks, that is isopentyl pyrophosphate and dimethyl allyl pyrophosphate, just now what I said. And it is denoted as IPP, isopentyl pyrophosphate, and dimethyl allyl pyrophosphate, which are used to make isoprenoids. Diverse classes of over 30,000 biomolecules such as cholesterol, heme, vitamin K, coenzyme Q10, and all steroid hormones are also produced by this pathway. So these 2 chemicals, these 2 structures, you should very much important for you to remember. What are they? They are isopentyl pyrophosphate and dimethyl allyl pyrophosphate. Both of them are having only 5 carbon atom compound. They are pentane derivatives. You can see this. This is the structure of This is the structure of mevalonic acid. So as I told, you should know mevalonic structure, mevalonic acid structure. Then we will go to this isoprenoid units and what is the other structures, how they are formed. So first you see, this is the structure of, this is the chemical structure of mevalonic acid. So mevalonic acid, you can see that is a OH group and an acid group. The two OH group and an acid group and a methyl group are a substituent here in this long chain. And it has CH2, CH2, C, CH2, C double bond O, OH, that is carboxylic acid group. So 1, 2, 3, 4 straight carbon atom, and you can say butane molecules, and which is having a substituent of methane, and 2 OH group with an acid functional group, that is mevalonic acid. You can see there, that is both of them I have shown to know about the structure. You should remember this is the structure of mevalonic acid. And now you come to this slide. Here in this slide it is shown that in a bacteria, in a unicellular bacteria or eukaryotic bacteria or eukaryotic cell, this reaction takes place. How? You can see that acetyl-CoA is converted into acetoacetyl-CoA by means of enzyme acetyl coenzyme and thiolase. Why you have written acetyl coenzyme once again? Because two molecules of acetyl CoA in the presence of thiolase enzyme, it is converted into acetoacetyl CoA. So acetyl CoA have only two carbon atom, and one more molecule of acetyl CoA, when it is added, it becomes 4 molecules of carbon atom. So you can see 4 carbon atom compound acetoacetyl CoA, and acetoacetyl CoA is converted into HMG CoA with an enzyme HMG CoA synthetase, and then HMG CoA is converted into mevalonate, that is mevalonic acid, and mevalonate is converted into mevalonate 3-phosphate with the help of with the action of an enzyme mevalonate 3 kinase, and then that mevalonate 3-phosphate can be converted into mevalonate 3,5-biphosphate, that is blue color structure which I am just reading from the slide, and then it can be directly converted into isopentyl phosphate. Isopentyl phosphate is our compound which I told, isoprenoid 5-membered carbon atom containing compound. We are nearing to the product which we needed, isoprenoid unit, that means isopentyl phosphate. You see, another channel of mevalonic acid can also be converted into mevalonate 5-phosphate by means of mevalonate 5 kinase, 3 kinase and 5 kinase. There are 2 enzymes in 2 pathways, they can be acting in a natural plant. So you can see even plant or even in bacteria, and this mevalonate 5-phosphate again it can enter in, it can be reacted by 2 enzymes, different pathways, different line of way. One is mevalonate 5-phosphate decarboxylate. When you add it, decarboxylation takes place, immediately it gives a product of isopentyl phosphate. But if you are using again kinase phospho, that it means phosphomevalonate kinase, if you are using, it is again phosphorylated. Kinase means phosphorylation, it is going for another addition or another reaction, another product is going to give. So when you are reading pyrophosphate, mevalonate pyrophosphate, it's an important product which you are getting, mevalonate pyrophosphate. You see this side already we have isopentyl phosphate, and both of them, they are having different enzymes are needed, because isopentyl phosphate have to be added with a kinase to get pyrophosphate, that is isopentyl phosphate kinase. But if you see mevalonate pyrophosphate have to be decarboxylate also, because already it is pyrophosphate, it has to be decarboxylate. So only thing is, the student have to remember, there you are first decarboxylase you are using, and then you are using the kinase. Here you are using first your kinase and then you are going for decarboxylase. Very simple. Once you see that, it will be very easy for you to know, because the enzymes are one or other, because it is natural. We cannot go for many adjustments. It is natural. It will go in only one streamline. So you can see that mevalonate pyruvate decarboxylate, when you add here and when you add isopentyl phosphate kinase, when you are using, automatically you are getting a product of both of them will give a unit product, that is isopentyl pyrophosphate, IPP. Isopentyl pyrophosphate can be even interconvertible by means of isomerase enzyme. What isomerase enzyme? Isopentyl pyrophosphate isomerase enzyme can give rise to dimethyl allyl pyrophosphate. So the student should name of the compound. You should be thorough with your study. That is, there are two products, two isoprene units which are very much responsible for various production of steroid, terpenoids, and hormones and heme and very other compounds, cholesterol, everything. If it is produced by means of two compounds, what are they? They are that it means isopentyl pyrophosphate and dimethyl allyl pyrophosphate. So you can see here, this is also again in my class or in my handout, in my PPT, you can see repeated slides. These slides are made for only students for their easy study, not for just for, I am not going to present. This is a class, it's a normal class, I am just recording for the student. So it will be, repetition will be there just for your study purpose. It will be easy. Only one concept. You see here, the acetyl CoA is converted into acetoacetyl CoA with the help of enzyme thiolase. But here it is not shown directly with the thiolase cannot directly give acetoacetyl CoA. You need one more molecule of acetyl CoA is needed. That is what in the previous slide I was shown. And then if you see HMG CoA synthetase, you will get the HMG CoA, and HMG CoA is converted into mevalonic acid by means of HMG CoA reductase in strides. And by means of ATP cofactor, it can be converted, even involved by mevalonate kinase, it will give mevalonate 5-phosphate, and mevalonate 5-phosphate can be converted into mevalonate 5-pyrophosphate by means of phosphomevalonate kinase. And mevalonate 5-pyrophosphate can be converted into isopentyl 5-pyrophosphate by means of mevalonate 5-pyrophosphate decarboxylase. And afterwards you are using an isomerase. So after obtaining the isopentyl 5-pyrophosphate can also be interchangeable by means of dimethyl allyl pyrophosphate by means of isomerase enzyme. Understand? Isopentyl pyrophosphate isomerase enzyme. So this is again, after seeing the slide, it is completely data, one by step it is written. Just let me go through and let me make you to listen by means of audio. You can just listen what we have explained in that previous slide. The first step is condensation of two molecules of acetyl CoA with the presence of an enzyme thiolase to form acetoacetyl CoA. The next step will be the reaction of acetoacetyl CoA to another acetyl CoA with the presence of HMG CoA, a synthetase to form HMG CoA. So you see, there are three molecules of acetyl CoA are involved in this reaction. So first one acetyl CoA react with another acetyl CoA and it gives acetoacetyl CoA, and another acetyl CoA react with this acetyl CoA with the presence of HMG CoA, it gives HMG, the synthetase, it gives HMG CoA. And this HMG CoA reductase serves as an enzyme form the mevalonic acid, and mevalonate reaction occurs in the cytosol. And you can see, as your mevalonate, that is reduced mevalonic acid, phosphorylated, it will now form 5-phosphomevalonate with the presence of mevalonate synthetic kinase. It will undergo another phosphorylation with phosphomevalonate kinase and will eventually 5-pyrophosphate mevalonate. And the mevalonate 5-pyrophosphate decarboxylase is the next enzyme that will promote the formation of isopentyl pyrophosphate from mevalonate 5-pyrophosphate. So the last step is the isomerization of isopentyl pyrophosphate to dimethyl allyl pyrophosphate. So you see, I am always repeating the two structure. The student should remember there is the two structure. What are they? They are isopentyl pyrophosphate and dimethyl allyl pyrophosphate. They are isoprenoid units. They are having 5 carbon atom compounds. One is isomer of other. So that is the two components which are responsible for our acetyl pathway or mevalonate pathway. These two units are very much responsible for various production of secondary metabolites like steroids, terpenoids, and hormones and various other products. And so it's responsible for formation of terpenes. Here I have mentioned, also known as HMG-CoA, 3-hydroxy-3-methyl-guttyryl-CoA or mevalonate dependent root, and precursor of terpenoids, terpenes and steroids production. See, this is also the structure. When you see the structure, what is the reaction which we have studied? Just it is shown in a structure. You see, acetyl CoA is very simple to write. CH3, C double bond O, S, COA. If you write like that, that is enough. It is structural form, it is written. CH3, C double bond O, CH2, C double bond O, S, COA, that is acetyl CoA. So how many carbon atom is there? You can see there is 1, 2, 3, 4 carbon atom. And again you can see another coenzyme is added and you are getting HMG-CoA. That is the structure. There you are getting OH group, and this HMG-CoA is converted into mevalonate or mevalonic acid by means of HMG-CoA reductase and also cofactor NADPH-NADP conversion, formation of mevalic acid, and then formation of 5-phosphomevalonate unit kinase. So by means of mevalonate kinase, mevalonic acid or mevalonate is converted into 5-phosphomevalonate phosphorylation. So 5-phosphomevalonate by means of kinase. So next one you can see, after getting 5-phosphomevalonate, it is converted into 5-pyrophosphomevalonate by means of phosphomevalonate kinase. And you have a cofactors also, ATP conversion of ATP to ADP, and this is the formation of 5-pyrophosphomevalonate and formation of isopentyl pyrophosphate. Now how the 5-pyrophosphomevalonate is now converted into the 3-isopentyl pyrophosphate by means of an enzyme mevalonate 5-phosphate decarboxylase. So you can see the structure. It is also a cofactor. ATP is converted into ADP, and also removal of carboxylic acid or carboxylate, that is the decarboxylation takes place, and you will get 3-isopentyl pyrophosphate, which is the product which we need, 5-membered carbon atom compound, and it is the main compound which we have received it. And now you can see that this compound, that is 3-isopentyl isopentyl pyrophosphate, is converted into dimethyl allyl pyrophosphate. So they both are interchangeable, they are isomerase, they are isomers. Isopentyl pyrophosphate isomerase is used, so that you can see 3-isopentyl pyrophosphate is converted into dimethyl allyl pyrophosphate. So you can see this slide. For the student purpose I have shown, that is chemical structure is written. There is a double bond, CH2 double bond C and CH3, and then CH2 CH2O PO2 PO3 and 3 minus, that is we have shown the electronic configuration, and this can give the phosphate can give double bond shifting, that means isomerase CH3 and C double bond, there is a CH3 and dimethyl and allyl, and you can see that CH2O and phosphate. So dimethyl allyl pyrophosphate. This can be written in the below. You have seen the structure. The 5 carbon atom is responsible for the formation of terpenes. I have written a line and I have shown both the sides. I have shown the structure, and it is easy. That's just, you can see there is a Y shape and just like a tail, and here also. So there is a head and a tail for this structure. That is why these isoprenoid units, always they used to say in terpenes, a tail will be connected with the head, a tail will be connected with the head. In some cases only the tail will be connected with tail and head will be connected with head. So they are exceptional in the terpenes, and there are many compounds which are forming by that. So that is also, so we should know what is the tail and head in a terpenoid or in the structure which I shown, that is isoprenoid unit. So that is also I have added in these slides, because in the previous material which I gave to you to download, in that I have not added some 2-3 slides, and I just extra I have added here to give some explanation what is the tail and the head of an isoprenoid unit, and we will see in the next slide, coming slides. So now we are going to see that is terpene biosynthesis, formation of geranyl pyrophosphate. Up to now we have seen how 5-membered isoprenoid units are formed from acetyl CoA. Just a student should have that mind. You have to have a mind, a picture in your imaginary picture should be there always while studying, imaginary picture, or you should have some hints to write. When you are listening my lecture, better you can write something, you can have something, a paper or pen, and you can note it down, and then you can go for your hard copy and read, so that you will not never forget. The subject will be remaining. It is not necessary to study daily. You can have this and you can have in your mind as a storage. It is possible for you to read regularly. So you see here, formation of geranyl pyrophosphate. It is dimethyl allyl pyrophosphate and isopentyl pyrophosphate. These both of them, both of them we are joining together. So 5-membered. 2 5-membered ring structure joined together, and you are getting a 10-membered ring structure, that is geranyl pyrophosphate. So dimethyl, you can see the blue color and the light blue color. They both of them, that is a tail is connected with the head of the another isopentyl pyrophosphate. You see, the head of the isopentyl pyrophosphate is connected with the tail of the dimethyl allyl pyrophosphate, and you are getting geranyl pyrophosphate. How many carbon atoms are present in the geranyl pyrophosphate? Geranyl pyrophosphate having 10 carbon atom. You have to remember that 2 5-membered carbon atom joined together, and we are getting 10 carbon atom compound, that is geranyl pyrophosphate. So this geranyl pyrophosphate can give rise to various 10-membered carbon atoms, which is terpenes, are available in the plants like these structures. You can see in this slide I have shown that this geranyl pyrophosphate, by means of removal of water molecule, and it can be decarboxylation, it can give rise to our hydrolysis, it can give rise to geraniol in the rose and geranium oil, and reduction can give citronellol in the rose and geranium oils, and oxidation can give rise to citronellol, that is an aldehyde in lemon oil. That one is alcohol, this is an aldehyde, so citronellol Al in lemon oil. And you see the geranyl pyrophosphate can give rise to even alpha terpeneol in juniper oil, and also by means of hydrolysis it can give rise to terpene hydrate, a common constituent in cough medicine. And also you can see limonene in orange can also be obtained in lemon oils, and also by oxidation, and then again it is reduction, it can give rise to methanol in peppermint oil. So this is the some products. There are many, still more. You can see, you might have studied many terpenes like camphor. There are many terpenes are there, which are also produced by means of monoterpene, diterpene, sesquiterpene. There are many terpenes are there. So even that terpenes are also all produced from this geranyl pyrophosphate. So see now, formation of fercinyl pyrophosphate. What is fercinyl pyrophosphate? Again another isopentyl pyrophosphate we are joining with geranyl pyrophosphate. You will get a 15-membered compound, that is fercinyl pyrophosphate. You see, you are taking geranyl pyrophosphate, you got by one molecule of isopentyl pyrophosphate and one molecule of dimethyl allyl pyrophosphate joined together, and you got geranyl pyrophosphate. And geranyl pyrophosphate, when you add with isopentyl pyrophosphate, you are getting again the tail of that geranyl pyrophosphate is connected with the head of the isopentyl pyrophosphate, and you are getting a 15-membered farnesyl pyrophosphate. So this farnesyl pyrophosphate, it has 15 carbon atom as shown in the picture. You can see there is 3 annular, it is shown like 3 annular, 4 methyl groups, and it has 3 double bonds because 3 molecules of isoprene units are there. So that is what very easy for the students to remember the structure and to write, because 3 molecules of isoprene units, there should be 3 double bonds. And you can see there is only 4 free methyl group. Why? Because the 2 of them are joined in the tail, and the free one, the first one only will be 2 dimethyl will be free. So 4 free methyl groups will be there. So easily you can remember that is 15 molecules, 15 carbon atom containing a compound which is produced by means of adding one molecule of isopentyl pyrophosphate with geranyl pyrophosphate. We will achieve the farnesyl pyrophosphate. And this farnesyl pyrophosphate, 2 molecules of farnesyl pyrophosphate will be added for the formation of cholesterol. We are going to study about the cholesterol, how it is formed. So cholesterol is a very long structure. It has more than carbon atom is 28 carbon atom and substituents are there. So you should have that much carbon atom should be there. So you see here, and you are getting more than 30 actually in cholesterol, you can see. So you can see by the substituent. You can see that farnesyl pyrophosphate, 2 molecules when they are joined together, and here only there is a change, is tail to tail it is joined. It is not head to head it is changed, tail to tail it is joined. So you can see that is what, how many double bonds are there in a farnesyl pyrophosphate? 3 double bonds and 4 free methyl groups and 2 molecules of farnesyl pyrophosphate. When you are joining with tail to tail, what will happen? What will happen? Immediately you will not lose all the 4, even 4 methyl group will be, again it will be present in the 2 molecules. So 8 free methyl groups will be there, and 8 double bonds will be, not 6 double bonds will be there. And how many carbon atoms will be there? The compound which is produced, squalene, will have 30, 15 plus 15, 30 carbon atom compound, squalene. Squalene is a precursor or an in-between product, an intermediate product to produce the cholesterol. That is, everybody knows. When you study cholesterol synthesis, even synthetic chemistry, there will be always you can see this squalene. The squalene is in biosynthetic pathway also. The squalene is produced in the presence of squalene synthetase, is an enzyme which will be producing the squalene structure. You can see very clearly. So 30 carbon atom, long chain, and you have to remember there is 6 double bonds and 4 free methyl groups will be there. And why it is there, you should know that is tail and tail are joined. What is this tail and head? These 3 slides I have just made and incorporated to give some idea. Now the student should not have any confusion about what is this tail and head of an isoprene unit. This is the isoprene structure. If it is board is there, I might have written and shown, but anyhow this structure is enough for you to know, because basic chemistry, this is an advanced pharmacognosy. So when you see, you have studied already the chemistry base, so you may be knowing very easily. 5 carbon atom containing compound, it is isoprene units, 2 methyl butane, 1 2-diene. And then you can see that this is the structure which we have shown. This part, the first front part, that is shape which is open, it is called head, and the tail, very easily the tail, you can see the aeroplane like tail, you can remember. So one unit which contain 5 carbon atom, isoprene unit contain 5 carbon atom. So isoprene rule means the head and tail. and the tail will be connected with the head of another molecule. So you will get this type of, so you can see the head and tail connection. So this you have done already just before. What you have got? One is two isoprene unit joined together and you got the geranyl compound. Geranyl pyrophosphate, isopentyl pyrophosphate with dimethyl allyl pyrophosphate, it gave geranyl pyrophosphate. So that is 10-membered carbon atom compound. And then you can see the 10-membered, 15-membered carbon atom also we have formed by means of 3, that is you have taken 3 molecules of isoprene unit, tail to head joining, you are getting a farnesene or farnesyl pyrophosphate. And you can see even sometimes cyclization of a compound and you are getting various isoprene unit, which you have just now we have seen. Even geranyl pyrophosphate can give rise to terpenes, various terpenes, limonene, citronellol, or even camphor. These all of them are produced from this isoprene units. And this is the structure of the precursor, that is squalene. Triterpene is a precursor for steroidal molecules of squalene, which we have discussed already. So once you have to take the structure and write in form of CH3, CH2, CH, like that you have to write in every double bonds and what is in the junction, whether it is C or CH or CH2 or it is the annular CH3, that you have to write in the form of chemical structure, so that the student will understand how many carbon atoms are there and how many hydrogens are there. It is necessary for you to write the structure and the chemical name yourself. And you see, this is the overall cholesterol synthesis, how it will be formed. Same like acetyl-CoA is converted into HMG-CoA. I have put only 2 lines, arrows. But you should know, remember what is the previous slide what we have discussed. We discussed clearly in the previous slide. We told acetyl-CoA will join with another molecule of acetyl-CoA and it will give acetyl-CoA. Acetyl-CoA will be joined with another acetyl-CoA and it will give HMG-CoA. So that is what it is, just put on arrow. And HMG-CoA is converted into mevalonate, and mevalonate is converted into activated 5 carbon atom compound. What is that 5-membered carbon atom? That is isopentyl pyrophosphate. And this isopentyl pyrophosphate will join with dimethyl allyl pyrophosphate and gives 10 carbon atom compound, that is geranyl pyrophosphate. Geranyl pyrophosphate again add with an isopentyl pyrophosphate and you will get an 15 carbon atom activated compound, which is called farnesyl pyrophosphate. Farnesyl pyrophosphate will be converted when it will be added with another molecule of farnesyl pyrophosphate and they will join, tail to tail join, 15 carbon atom, 30 carbon atom compound, which is known as squalene open chain. And this squalene will be converted into lanosterol and lanosterol will be converted into cholesterol, and in between lanosterol is not directly converted into cholesterol, it will be converted into dehydrocholesterol and then it will be converted into cholesterol. That is what it is missing there in arrow. You can see now very clearly what we are told. I am missing all these things I have written in this slide. You can see that is acetyl-CoA and acetyl-CoA, 2 molecules is acetyl-CoA, another molecule of acetyl-CoA, it gives HMG-CoA. HMG-CoA is converted into mevalonate by means of the intermediate cofactors and also the enzymes, and next it is converted into isopentyl pyrophosphate. Isopentyl pyrophosphate is converted into dimethyl allyl pyrophosphate. Both of them they join together and they give geranyl pyrophosphate, the 10-membered carbon atom compound. And then geranyl pyrophosphate will join with isopentyl pyrophosphate and it gives the farnesyl pyrophosphate, which has 15 carbon atom compound. And this farnesyl pyrophosphate, 2 molecules, they are just condensed together in the cofactor, presence of enzyme and also cofactors, and it is converted into squalene and they are joined in the form of tail to tail form, so that it is easy for you to remember. There is 8 methyl groups, free methyl groups are there, and also you can see there is 6 double bonds should be there with 30 carbon atom compound, that is squalene, open chain squalene long chain. And this open chain squalene will get cyclized by means of, it is changed into NAD by means of the cofactors, and it is giving rise to squalene epoxide, and then it will be converted into lanosterol. Lanosterol, you can see it is an extra, it has 3,2-methyl groups, and also a double bond is not present in the first or the second ring structure. So, and also extra 3 methyl groups will be there in the lanosterol, and that will be converted into 7-dehydrocholesterol as shown in the picture. 7-dehydrocholesterol is coming to one more double bond is extra will be there, that is why 7th position dehydrocholesterol. Once you remove that double bond, you are getting one double bond in the second structure and as well as 2 annular methyl group, and if you have OH then it is cholesterol. Cholesterol structure is a very important structure to give various other formation of other compounds and other structures which will be formed. So cholesterol is one of the important structure which we have to study. So you can see here the cholesterol give rise to that is pregnenolone, and pregnenolone can give rise to 7-hydroxypregnenolone, and then it can give rise to dehydroandrosterone and epiandrosterone, and it can be converted into androsterone. The androsterones can convert it into estrogen and also testosterone. Estrone and estradiol also produced through them. And when you see this, progesterone also comes from progesterone, and then progesterone can give rise to all the mineralocorticoids, corticosterone, cortisol, and comes aldosterone. So you see here the structure which you have already studied in the chemistry, and so you have to know about what is the basic structure of an steroid, because cholesterol is having the basic structure of steroid. Please, students should know what is the basic structure of steroid. You might have studied the heterocyclic compound and the steroidal compounds in your organic chemistry by means of telling that there is 3 6-membered ring and 1 5-membered ring, which is denoted as A, B, C, D, and there will be 2 annular methyl groups, and a substitute will be starting from that is 17th and 18th position, and then the starting from the particular. The numbering also very important about the cholesterol. So once you study the numbering and you know what is the substitute and what is the difference between progesterone, what is the structural difference in the estrone, and also what is the structural difference in cortisol. So it is very simple to study, but you have to write and study clearly. Then only you know what is the substituent, what is the functional group differences in this aldosterone and progesterone and corticosteroids. These all steroids are having similar basic structure of steroid. Only thing is their substituent, how many OH may be present, double bond O in the positions, and what is their positional various structural activity relationship will be differ what you studied in synthetic chemistry. So note it down, these structures, and very important to know what all the compounds can be formed from the cholesterol. So you know the cholesterol how it is formed, and from cholesterol how they are formed. You just imagine, see, for example, you have to practice like me how you are going to prepare this compound. Very simple, in your mind it should come. It is by means of acetyl pathway or mevalonate pathway. Acetyl pathway means immediately you should know that acetyl CoA is joined with another acetyl CoA. It gives acetyl CoA. Acetyl CoA will join with one more molecule of acetyl CoA, and it gives HMG CoA. HMG CoA is converted into mevalonate. Mevalonate is converted into isopentyl pyrophosphate. Isopentyl pyrophosphate can be converted also into isomerase by means of dimethyl allyl pyrophosphate. 2 molecules, they both will form and they will give a 10-membered compound, that is geranyl pyrophosphate. Geranyl pyrophosphate will add with another isopentyl pyrophosphate and gives ferrinyl pyrophosphate, which is 15-membered carbon atom. 2 ferrinyl pyrophosphate compound. In the tail-to-tail joining, it may give squalene, and squalene will cyclize and it gives epoxide squalene, and it will give into lanosterol. Lanosterol is converted into dehydrocholesterol. Dehydrocholesterol is converted into cholesterol, and cholesterol can also give rise to various system of compounds like prednisolone and progesterone, and also it can give estrone progesterones, and also it can give rise to cortisols and aldosterones. You can just find out the structural difference and easily you can write. It will be more than 10 pages you can write. If they are asking any type of synthetic pathways, anything about synthesis, if you write, they can write many enzymes, and also theoretically you can write, also structure wise you can explain, and it will be very easy for the teachers, will be very appreciated, and they will give you good marks. So just you should understand that one and you should go through. And now phenolic acid compounds are also, just that is because I want to just give some phenolic compounds, I have not taken much detail about phenolic compounds step by step, but they are also involved in this type of ring structure. So what is phenolic compound? So phenolic compound, these are classes of natural occurring compound with one or more phenolic compounds or benzene ring with OH group. As is shown in the picture, you can have a benzene ring and also it has many OH group. That is why it is phenolic compounds, which are usually flavonoids, and also it is about tannins and flavonoids. They used to have this type of flavonoids. They are having these type of structures, and they have many uses apart from the many drug uses are there. Especially quercetin, a typical flavonoid, a natural phenol, is also having this in example. And biosynthesis of phenolic compounds, equally most of the natural phenols are derived from secondary plant metabolites of succinic acid pathway, mevalonic acid pathway, or both. Even both of the succinic acid pathway and also mevalonic acid pathway is also possible to have both the links and to form a particular secondary metabolites are also formed. The phenolic compounds are formed. And you see, this is the structural, this is one type of a cycle which you have to remember, that is general metabolism, which is made by succinic acid and alpha phenylalanine. It converts succinic acid. First succinic acid is formed and alpha phenylalanine is formed, and then it comes an intermediate product of cinnamic acid, and this cinnamic acid, it gives rise to there is caffeic acid, and caffeic acid is also even it is coming from paracinnamic acid, and coumarin and soralin is also formed, and ferulic acid can also be formed. Apart from that, you have to remember that is the dihydroflavone and chalcone is also formed by flavanone and flavone and flavanol. These all are some of the product which can be also formed from this various synthesis which can be produced. So you have to remember these structures and see here, and these are usually applicable in where it is present. Phenolic compound more is very good example for phosgram, a kind of bean, and you can see this contain three products what you have seen. Cafe, that is caffeic acid, not caffeine acid, this is caffeic acid. Caffeic acid, caffeine is xanthine derivative, that we will be studying different structure. So this is caffeic acid and protocatachic acid and also coumaриc acid. These all are present in horse gram beans, and these also some of them which passes through the our aromatic amino acid pathway, succinic acid pathway. It will pass through so that it will get the aromaticity. So next class we will see about this tracer technique, because tracer technique is also a topic which has to have some more explanation. It was theoretical knowledge only I can give, because tracer technique is a very important technique which can be followed in various methods are available, and we will have the discussion in the next class. And anyhow, for being with me, and also we will continue in, I hope this Monday we will be having a class of pharmacognosy in the morning, and so that we will continue. Thank you very much. Bye.